All right, so now we move into chapter 8. It deals with vapor power cycles. This is the way the electricity is made for the majority of the electricity in the world. Okay? You boil a substance like water, make steam, pass it through a turbine. The turbine has a shaft. It drives an electric generator, produces electricity. You are a part owner because it's a CPS Energy is owned by the citizens of San Antonio. It's a municipally owned utility. It's a very large, I think it's the largest in the United States, municipally owned utility. That's pretty unique for San Antonio. Covers pretty much all of Bexar County and a little bit of surrounding counties, but very little. And this is one of their coal-fired plants down at Lake Calaveras. They're making electricity there by burning coal. So if you burn coal, that's the way you make it, vapor power cycles. If you have a nuclear power plant, there's 4 nuclear reactors in the state of Texas, 2 up at Comanche Peak, 2 down in the South Texas project by Bay City. CPS is part owner of the ones down there. We get probably 30% or more. I think it's more than 30% of electricity we use every year from Bay City. That's nuclear. All right, so this is the way. Now, also you can burn natural gas, put it through a gas turbine. That's next chapter, Brayton cycle. And then after that, it's still hot. Use it to boil water to make steam, and then put that through a Rankine cycle, through a steam turbine. That's what they call a combined cycle. In the last 10 years, everybody's been building natural gas as your primary fuel, combined cycle plants. It's hot. It's been hot for the last 10, 15 years. Natural gas prices are really low. Why? Fracking. You get a lot of natural gas coming online. Really dirt cheap energy right now. So nobody's really going back to nuclear. Everybody's shifting away from coal. I think we know why. It's emissions with the high CO2. And everything's been natural gas combined cycle power plants. All right, let's press on. We're going to study the Carnot as a review. Carnot vapor power cycle. We studied in Thermo 1 the Carnot gas power cycle. Now we have the Carnot vapor power cycle. That was studied in Thermo 1. We'll review it. It's named after this individual, Sadi Carnot. Those are the years he lived. And when you get my age, you pay attention to how many years he had to walk on this earth. That's not that long, is it? So he did something we're still talking about, and every thermodynamics textbook talks about, uses the name the Carnot cycle. All right. So it's a copy translated to many languages. You can find it translated to English. I don't know what the French is, but it's reflections on the motive power of fire. At the start of the Industrial Revolution, it was novel. You could burn something to do what muscle, human muscle or animal muscle, used to do. Otherwise, if you wanted to lift something, move something, it was human muscle or animal muscle. Now, you had a machine, you could burn something, you would turn something, you could lift something. That was very unique, very unique. And so you burn something to basically have mechanical power, the motive power, motion, power, mechanical power. And what is this reflections? He's thinking about it, pondering, thinking, hey, now that I see that this heat engine works by burning something, how can I make it more efficient? Because believe me, the first steam engines were really inefficient. They had to burn a lot of coal or a lot of wood to do a little work. So a couple things he came up with, 1 minus TL over TH, and we use that equation to this day. That's the maximum thermal efficiency of a heat engine, where all of the heat into the heat engine is brought in at the high temperature, and all the heat rejected is rejected out at TL, the low temperature. And then it made the conclusion, it really doesn't matter if you have water or if you have a refrigerant or some other novel fluid. Look it, they all have the maximum thermal efficiency. That's kind of unique. These are at least 2 of the big ideas that came out of his work. We're also going to talk about the Rankine cycle, named after this individual, William John Ruquin Rankine. I'd probably mispronounce that name, but these are the years he lived, again, early in the Industrial Revolution. These are many years he lived on this earth. Too short in my opinion. I'm already over both of those. And we're still talking about what they did in their short lives. So this is great accomplishment. They was in Scotland. There was a lot of heat engine developments, steam engine developments up in that part in Scotland. He not just in power production. He was in metals, metal fatigue, railroads. It's civil engineer. But he published in 1859 a manual on steam engines and other prime movers. Here's a copy of the cover page. And that's one reason why we honor him with his name on this cycle. Also, not only did you see that for the cycle, but you saw it for the temperature scale, the Rankine temperature scale. Okay? And then there's a guest lecture series or award given in geomechanics that his name. So he's well-rounded, a huge contributor in science and engineering. So let's go back and review. Somebody says, how are we going to accomplish this Carnot vapor power cycle? Well, two things you want to do. You want to be able to sketch out the four components that make up the Rankine power cycle. So you have a fluid flowing from one component into another, then out of that component into another, and then out of that component to another, and it goes like that. So what are our four components? Well, one you might call a boiler. What's the purpose of the boiler? You're going to bring some heat in, Q, brought in to the boiler, Q sub B. Now we use the lowercase q subscript B. Subscript B is for boiler. Why lowercase q? Isn't that lowercase q is q dot divided by m dot? Yeah, and the dots cancel. You don't put a dot on that lowercase q. And what would be the unit? So how many kilojoules of heat into the fluid flowing through it per kilogram going through, kilojoules per kilogram. All right, then you go down and you have a turbine. What's the purpose of the turbine? Well, it has a shaft coming out, and its purpose is to produce work. W subscript T. What units? Kilojoules per kilogram. Now, I'm going to stay with the sign convention that the heat transfer in is positive, but we know that this next device is a condenser, and it doesn't have heat transfer into it. It has heat transfer that's rejected out of it to the surroundings. But we're going to leave it like this. We're going to put QC. This is the positive direction for the heat transfer. We know it's out, but we're assuming positive in. What do you think the sign should be, positive or negative on this QC when we calculate it? It should be negative. This should be positive. This should be positive. All right. The last one, you can call it different things. I'm just going to call it a pump. Now, it's really not a good pump, but it's a pump nonetheless. We'll call it a pump. And here, what we're going to do is we're going to say, A, the work coming out of the pump. Well, does a pump need shaft work supplied to it, or does it produce shaft work? It needs it supplied. Do you think we're going to have a negative? Yeah, this will be computed as something like negative 10 kilojoules per kilogram in our bookkeeping. So you make a schematic of the components. You know the fluid is flowing out of the boiler into the turbine. So you're going to do either a CM analysis, closed mass analysis of the boiler, or a CV analysis of the boiler. Which one do you think? It's an open system with a control volume. It's not a closed system with a control mass. Again, open control volume. That's what we're going to do. I forgot to introduce our states. We'll call this state 1, state 2, state 3, and state 4. So what we would do is we would have a control volume which cuts the pipe at 4, goes around the boiler, cuts the pipe at 1, and cuts through that heat transfer. Then, so I have heat transfer across the boundary of that control volume coming into the boiler. Now, you have to be able to do a first law analysis, not only for the boiler, the next one for the turbine, the next one for the condenser, and the next one for the pump. What are we going to do those for? Because we want equations for QB, WT, QC, and WP. Right? Right. So Let's take a look at that boiler. What is this equation? The most grand, glorious, longest equation for energy balance of a control volume at Thermo 1. And if you took the class from Phenol, Creamy, or whoever taught it, they want you to start there. True? Well, guess what? You've started there enough times that I'm going to review the starting there, but then later, you know, it's kind of done this a few times. I've analyzed a few turbines in my life, right? The same with you on homework problems. And so you could speed up the process. But why would this term be 0 when we apply it to this control volume surrounding the boiler? Steady state. Why is this term 0? Because a boiler is a heat transfer device. It's not a power-consuming or power-producing device. Can you explain that to me again, Professor? No, just go back to Thermo 1. All right. Now, why do we not have a sum? Why do we just have one m dot? Because it's only one in, one out. They're the same. Why are there negligible changes in kinetic, negligible changes in potential energy? Those are traditional assumptions, unless you're given more information about the speed or the elevation change. And yes, in Thermo 1, we do. Okay, and then you find out, you got to be careful with your units. And you got to usually you find out that those are small compared to the change in the enthalpy. Professor, why don't we have U's here? I think it's U's. It's a typo. It should be U's, not H's. Thermo 1 again, right? It has not only the internal energy, but it has the flow work, that PV term. Very important that we have H's there. So now what was the change between that first equation and this equation? Why did we go from cap Q dot to lowercase q without a dot? Yeah, that's right. This is divided by m dot. That's lowercase q without a dot. And now, if you wanted to, you could put a subscript b on it because we're focusing on the boiler. B on it for the boiler, but this one I should have struck the 0, right? But when we strike them and we arrange with state, the inlet is state 4, true. The exit is state 1, true. And so that's how it goes from inlet I to exit 1. Okay, and then we arrange. Take a look at this. Does it look fine? I always pause because I can have a sign error. I could have a sign error. Okay, think about this. After it comes out the boiler, what do you think about the temperature here? Do you think it's hot? It's higher temperature typically, or higher energy content typically, compared to what comes in here. So H1 is typically greater than H4, or all the time. Otherwise, it's a very poor boiler. Enthalpy is higher. Okay? All right. Let me ask this question. What's our standard assumption through a heat exchanger like a boiler about the pressure change? Is P1, the standard assumption, is that it is either greater than P4, equal to P4, or less than P4? Answer either A, if you think P1 is greater than, answer B, if you think it's equal to, or answer C, if you think P1 is less than P4. Everybody in? All right, let's see how we're doing today. Well, the standard assumption that there's no pressure change in heat exchanger. That's our standard assumption. So, all right. Now, what's a standard assumption about the outlet condition of the fluid at state 1 for a Carnot vapor power cycle? We're going to say that this is saturated. Here, I'll give you an easy one. Either answer A or answer B. Answer saturated liquid if you think it's A, or saturated vapor if you think B. What is it? Saturated liquid, answer A, or saturated vapor, answer B for state 1. You can answer C, which is I don't know. State 1. State 1. That's this state coming out of the boiler going into the turbine. Everybody good? Let's go ahead and stop. Hopefully that's a little confidence booster. Yeah, that helped a lot. It's saturated vapor is a standard assumption in the Carnot vapor power cycle. Okay, what do you think state 4 is? Saturated liquid. Because it's constant pressure, did the temperature of the fluid change? What is the relationship between, there's another clicker question. Come on over here. T4 and T1. Is T4 greater than, equal to, or less than? Answer A, answer B, or answer C. How does T4 and T1 compare? Is T4 greater than T1, equal to, or less than? All right, so again, what was the condition of the fluid coming out at state 1? Wasn't it saturated vapor? And then what's it? Saturated liquid. And the pressure 1 is equal to the pressure 4. It's constant pressure. So the temperature, both of them are the saturation temperature oops, I marked it wrong. They're the equal. They're equal. They're both the saturation temperature at that pressure. One of the things about the Carnot cycle is that all of the QB, all the heat coming in the boiler, has to all come in at the same temperature, TH, the high temperature. Maybe I should have done a deeper review of this, huh? I'm okay? All right, let's keep going. Well, you have to jump and do the control volume analysis of that turbine. Steady state. Does a turbine supposed to have heat transfer? It can, but our standard assumption is it doesn't. And that doesn't change kinetic or potential energy, the same mass flow rate in and out. So you boil this down to here. Actually, I needed to drop off the heat transfer. And so now the work out of that turbine is equal to H1 minus H2. Does this equation look okay? Professor, it's a lot to memorize. No, it's not a lot to memorize. It's not a lot to memorize. Right? All I have to do then is start changing state numbers. Oh, call this state 4. Call that state 8. And then you're all discombobulated. No, don't memorize. All right, so this should be positive. Is this a positive quantity? Which H is higher? Is H1 higher than H2? Yeah, the enthalpy, the energy content coming in is higher than going out because some of it was converted into work. All right, energy transferred out. Do the same for this condenser. Again, we go slow. What direction are we going to assume for the heat transfer in the condenser? Stay with the traditional sign convention in. We know that this anticipated to be a negative answer, maybe negative 50 kilojoules per kilogram or something like that, because we're assuming it in to stay consistent. Does this look okay after you do the math? Is it H3 minus H2? If H2 is greater than H3, won't that be negative? Yeah. And the enthalpy at 2 is higher than enthalpy at 3. We'll reinforce that in a second. But every now and then, this gets a little confusing because which is my direction for this Q sub C? Oh, it's into the condenser. I anticipate a negative answer. Likewise, we go to the pump. And so this is the pump, the pump. What about the pump? Is there any heat transfer? No, that's negligible. And so now we have the work of the pump is equal to H3 minus H4. I slow down. I anticipate this to be negative. That's negative if H4 is greater than H3. Is H4 greater than H3? Yeah, it is. All right? All right. So what you want to do when you solve a problem, make a good schematic. Boiler, turbine, condenser, pump. Introduce the numbering of your states. State 1, state 2, state 3, state 4. Boom. Then basically put in a property diagram to help you organize your thoughts A common one is a temperature entropy diagram. Oh, I haven't seen that. Well, it's your old friend, your long-lost old friend. Go back and review a little bit about the property diagram, the temperature entropy diagram. When you have steam, there's a nice dome like this. All right. What's at the top of the dome? What's that point called at the top of the dome? Critical point. CP, critical point. All right. Now, every point along the line to the right of the critical point on that dome, it's either saturated liquid or saturated vapor. Clicker question. Are these all states saturated liquid or saturated vapor? Answer A or answer B. Is it saturated liquid or saturated vapor on the right side coming down from the critical point? All right, I'm going to stop. I don't give you a lot of time. It's either you know it or you don't, right? It's more of just what is an observation of what it is. All right, so all of those are saturated vapor states going down. So it's all saturated vapor. Okay. On this side over here then, I'm not going to ask a clicker question. All of those states on the left side of the dome, are they saturated liquid or saturated vapor? They're saturated liquid. So now we're refreshed to what this dome looks like. What's the right side and left side edges of the dome? What does a line of constant pressure look like? Let's try to think about, hey, we had this pressure up here. It's the pressure high or the boiler pressure. What's a line of constant pressure look like? And then down here, the condenser, guess what? The low pressure is the condenser pressure. There's really only two pressures. 4 states are going to fit on 2 lines of constant pressure. So we have to be able to sketch what a line of constant pressure looks like. So what does a line of constant pressure look like on a TS diagram? So something like this hits the saturated liquid, comes across, constant pressure, saturated vapor, and then scoots up. There's another one, be like this, hits it earlier, scoots across, and then scoots up. One of those lines are for the high pressure. One of them is for the lower pressure. Okay, I think high or low, answer A or B. The line that's the highest in the TS diagram. Is that for my high pressure or my low pressure? If it's high, answer A. If you think it's low, answer B. And good job. It's the high pressure. Notice that when you have a higher pressure, the temperature in the boiler at which it's changing phase, isn't that the saturation temperature at that boiler pressure? And look at it right here. Isn't that T boiler, the saturation pressure at that temperature at that higher pressure? Yeah. So anyway, this is P of the boiler. All right. Then down here, this is the pressure in the condenser. That's a lower pressure. All right. So now you have this diagram. Where is state 1 on this diagram? Where is state 2? Where is state 3? And where is state 4? Well, you're doing a Carnot cycle, true? Are there any irreversibilities in this turbine? No, there are no irreversibilities in that turbine. How about for the pump? No irreversibilities. All of the heat, QB, is brought in at TH. Right? All of the heat, well, okay, negative brought in, Q sub C, is at TL. TL, this is TL low, this is T high up here. T high, T boiler, T low, T condenser. Okay. So can you show me where state 1 is? Who would like to volunteer? Where is state 1? Go ahead.
Saturated vapor at the bottom pressure.
At the high pressure. Right there is state 1. Coming out of the boiler at high pressure and it's saturated vapor, right? Now, the next easiest is 4. Where is state 4? Well, that was saturated what? Liquid. At what pressure? High or low pressure? High pressure. So guess where state 4 is? There's the process from 4 to 1 in the boiler. All right. Now the next hardest one is state 2. State 2. Well, you have to do a second law analysis of this turbine. Is there any entropy transfer with the heat? No, there's no heat transfer for the turbine. So if it's reversible, no entropy generation. What do you conclude about S2, S1? They're equal straight down on a TS diagram. That's why we like a TS diagram. So where is state 2? There. It's in a two-phase region. If somebody said, I need you to tell me what the quality is at state 2 just from this illustration. Can you give me an estimate? What would you give it to me? 75, 80%? Look reasonable? How did they do that? How did they do that? Well, it's the length of this line starting from this point over divided by the length of this line starting at the same point all the way to saturated vapor. Isn't it? Yeah. That's right. That's how you get that quality to be nearly, it looks visually 75, 80%. The length of those lines. True? All right. Let me dwell on that for a little bit. So S1 is equal to S of G at the high pressure pH or something, P high. Notation makes sense? That's how I'd get it. I'd get it off of the charts. Now I'd find it, okay, this is my S of G, the saturated vapor entropy at that high boiler pressure. Okay. Then somebody says you have an isotropic process, so S2 is equal to S1. But what's my equation to calculate S2? Isn't it S of F at the low pressure plus the quality at state 2 times S of G minus S of F? Oh, Professor, there's so much to memorize in this class. Come on, you know that equation, true? We'll use it so often. So this allows us to calculate numerically what X2 is. X2 is S2 minus S of F divided by S of G minus S of F. Does that make sense? Okay. This point right here is S of F. This point on the x-axis is S of G. What is this point? S of 2. What is the difference S2 minus SF? The length of that line. That's the numerator. The denominator, that's, I ended up erasing that, didn't I? S of F. S of G minus S of F. What is that? The length of that line. You can interpret this as the difference in entropies as a length on the horizontal direction on the TS diagram. Make sense? Okay. All right, the hardest one is state 3. The best way to do conceptually is think about what is the relationship between S4 and S3. They have to be the same. And so they're just piled up right there. So it's like S3 is right here such that you didn't really condense all the way. You just condensed far enough so that you got to state 3 such that you could put it through this magical pump that doesn't exist, and you would land up perfectly at state 4, which is saturated liquid at that high pressure. So what does this look like? It just looks like a box, a rectangle on a TS diagram. All the heat that's brought in is brought in at the high temperature. See that? From 4 to 1. All the heat that's rejected is all rejected at TL. That's a requirement for the Carnot cycle, both for the gas power cycle as well as the vapor power cycle. So you make a nice property diagram. So what did we do? Schematic, label our states, property diagram, first and second law for each device. To help organize, what you do is you would want to make a table when you're asked to solve for a problem like this. Let's solve this problem. So water is the working fluid of a Carnot vapor power cycle, what we've been studying. The boiler pressure is 8 megapascal. Right away, there were some students that messed up pressure conversions on the first exam. And let's do this. 8 megapascal, to help you here, is that 80 bar, 800 bar, 8 bar, 0.8 bar, answer A, B, C, D, or E, other. All right, then we'll show the results. Okay, now let's do this one. The condenser is at a pressure of 20 kilopascal. All right, same game now. Not going to give you much time. 20 kilopascal is at 0.02 bar, 0.2 bar, 2 bar, 20 bar, 200 bar. Answer A, B, C, D, E. Go. 20 kilopascal. Everybody's in, so we'll stop. And we show the results. That's pretty good. 0.2. 0.2 bar. You have to be able to do those that quick and that accurately, and that'll just save you a lot of time. Whatever. The student that was in my office earlier is like, I knew I made a mistake. Well, why didn't you figure it out? Your mistake in the test, you know? Instead of waiting for it to come back and get harshly graded and now want more partial credit. All right. Calculate the work developed by the turbine and the pump. Well, what did we have? You make that schematic. Here's my condenser. Here's my turbine. Boiler up here. Condenser and then pump. All right, let's draw that better. Boiler. Got it like that. Okay, we're going to do this. State 1, State 2. State 3, State 4. And what you want to do, if you wanted to get the work developed by the turbine, W out of the turbine, didn't we say that's H1 minus H2? You need the enthalpies. How about the work developed by the pump? You know that's going to be negative, W sub P. That's equal to the W3 minus, not W, H3 minus H4. We worked those out. And that's going to be negative, but I need the enthalpies. Likewise, when you come to part B, what's that heat transfer in the boiler? This is Q sub B, that's equal to H1 minus H4. I need the enthalpies. And here is my condenser, QC, which is H. I always mess this up because I got to go slow, because normally I want to avoid negative signs myself. So it's going to be the H 3 minus H2. All right. So what I recommend is you make a table of properties. All right. Maybe I make it over here. Here, I'll start it right here. And I would say at each state, I should be able to know or calculate the pressure. Now I would put up here some units. Look, if you like to put bar, put them all in bar. If you like to use kilopascal, put them all in kilopascal. Just try to get them in a consistent set of units. If you like, sometimes I'll do this. I'll put like temperature in degrees C and temperature in Kelvin as 2 columns, just to help me in my calculations. But you don't need 2 columns for temperature, and you don't need 3 columns for pressure. But if you're feeling squeamish or something, you could say, I'm going to have a pressure in megapascal, pressure in bar, and pressure in kilopascal, and I can't think of any other units that would make sense for pressure. But you could have, and then you could check yourself and recheck yourself. But it gets a little excessive. I would say 1 column of pressure, pick your units bar, fine. Then we're going to have quality, enthalpy, and entropy. And the game is now to fill that table. Fill it up. So the easiest is start, what is our pressure at state 1? Well, it's 8 megapascal. If you're working in bar, hey, I forgot. What should I put there for bar? 80. And then down at state 4, it's 80. And then what about this 20 kilopascal? I want to put it in bar and put it at state 2 and 3. 0.2 and 0.2. Did I do that right? Now what about the temperature? Well, you're going to have to use your table because you have to look up the saturation. Let's look up Tsat at 80 bar. Anybody want to read that off to me? 295.1. Down here, is it 295.1? State 4, saturated liquid at 80 bar. State 1, saturated vapor at 80 bar. They all, remember on the TS diagram, from 4 to 1 is at the same temperature. It's just changing phase. So that's right. How about the temperature 2? It's your Tsat at 0.2 bar. 60.06. How about at 3? 60.06. Yeah. This is kind of crazy. Think about it. This makes sense as you pass from the turbine down, you go from 295 degrees C down to 60 degrees C. All right, that makes sense. Okay, I can see that. The pump is going to take 60 degrees C and jack it up to 295 degrees C. Hey, we're going to talk more about that pump, but the ideal Rankine cycle corrects for that impossible to make, impossible to build, impossible to buy pump that's in this idealized Carnot cycle. All right. How about the quality? Well, what's the quality at state 1? It's saturated vapor. How about the quality of state 4? 0. These others, we're going to have to wait a minute. We're going to have to wait a minute. But how about the enthalpy at state 1? The enthalpy, is that H of G, and is this S of G at the 80 bar? Is that how I find it? And if I take a look in our tables, my S of G is 5.7432, and I didn't put units, kilojoules per kilogram Kelvin. And then enthalpy, H of G, 2758.0 kilojoules per kilogram. If you're following along, give me a thumbs up if you find those values. Very good. How about for state 4? Well, it's SH of F and S of F, isn't it, at that high pressure? So just move our fingers over a little bit, 3.2068, and then H of F is 1316.6 kilojoules per kilogram. Did I get those right or wrong? Okay, now we know that it's isentropic. So we know what S2 is. It's 5.7432, and we know what S3 is, 3.2068. So conceptually, you're doing a second law analysis to prove they're isentropic. Then I'll use to calculate the X at 2 is, we just wrote out that equation, is the S at 2 minus S of F at that low pressure, Sg minus S of F. Putting in our numbers, it'll be the 5.7432. We go up to our 0.2 bar to read across S of F, 0.8320, and then S of G, 7.9085 minus 0.8320. And then you calculate something. It's maybe, I have some numbers here on the next slide. Maybe it's 60, 70%. Okay. Once I know that, how do I get H at 2? Yeah, you have H at 2 is equal to the H of F plus the quality at 2 times H of G minus H of F. Somebody says, Professor, that's not right. It's H of F plus the quality at 2 times HFG. They're the same equation. Some books will put in an SFG column. This book does not put an SFG. They just put the HFG, the difference between saturated liquid, saturated vapor. So you can get that one. You could do the same thing. You get the quality at state 3, and then you get the enthalpy at state 3, just like you do it at 2. All right, once I know those, what I would recommend you to do is make another table, a table of your energy transfers. Now, this one is not per state, it's per component. What are my 4 components? My boiler, or if you could start turbine, whatever you like. Let's start boiler. Boiler, turbine, condenser. This is to help you. Tables help you avoid trivial errors. Condenser, pump. And the transfers of interest are my Q's in kilojoule per kilogram and my W's in kilojoule per kilogram. So right away you have the boiler, the turbine, the condenser, the pump. So I have 8 things. 1, 2, 3, 4, 5, 6, 7, 8. 8 entities that can go into that table. Now, luckily, half of them are zeros. 4 of the 8 are zeros. So do you think about the boiler? Is the boiler to promote Q or to promote W? What does it do? It promotes Q's, so the boiler has no work. And then what about the turbine? Well, the turbine's insulated. And then the condenser, there's no shaft in or out. That's 0 as well. And then the pump is insulated. So that's our standard assumption. So now that you have your H's, you just go in and you find, oh, I compute this. Now for the boiler, I should expect a positive answer for that Q. What about the condenser? That should be negative. Likewise for the turbine, I think, what is the sign that I'm anticipating? I should get a positive answer, and then for the pump, the way I've written, it's negative. Now, if you sum these 4, you'll get what they call the net. That's the sum of the 4. 2 of the 4 are zeros, so you're really just adding a positive number and a negative number, okay? But you will get Q net in that column. And if you sum the W's, you'll get W net in that column. At this point, I'd ask another clicker question. How does Q net compare with W net? Is it greater? Answer A. Equal? Answer B. Or less? Answer C. How does the net heat transfer, the sum of the Q's, compare to the net work, the sum of the W's? And we just take a look. And some of you remember from Thermo 1, energy is conserved. So what we have is just like a big block like here. You can forget the 4 components are inside the block. But if I have in over here, I have in there, I have out here, out there. I know that this is going to be a negative, this will be a negative, but don't worry about the signs, the math worked it out. But if I sum up the sum of the Q's in, the sum of the Q's in must equal the sum of the works out. Conservation of energy. Don't forget that, right? And so Q net must equal to work net. Professor, is that only true for the Carnot cycle? Would that not be true for a cycle where I had some inefficiencies in the turbine? Maybe I had isotropic turbine efficiency specified, thinking ahead later into the chapter. What do you think? How would you answer that question? Is this true? Is this true only for the Carnot, or is it true for every cycle? Clicker question? Should we do that clicker question or not? Is this? It's true for every cycle. Energy is conserved. And guess what? As an engineer who doesn't always have access to a solution manual, you're looking for ways to check your work. And as you check your work, what you can do is if you stop right here and you pause and you sum them up and they're not equal, you know what you should do? Go back and look for your error. That's it. All right. Now, once we've computed those, we compute what we call the answer, the metrics. Let's go back up here and take a look. What's the backwork ratio and the thermal efficiency? Well, what is the backwork ratio? It's the fraction what came out of the turbine that had to go back to feed the pump. And now because the pump is a negative entity, we want a positive answer, so put a negative in front of that negative to turn it into a positive. And this could be anywhere from 10 to 50%. As an engineer, you'd like a low backwork ratio. That makes sense. So what is the thermal efficiency of the plant? It's the ratio of what you wanted out divided by what you had to pay for to put in. You know, if you put in $1 and got out $3, that doesn't make any sense. So you have to like put in $3 to get $1 out. It's going to be a fraction. The thermal efficiency is less than 100%. So what do you put in and what do you get out? You want out the net work. And what do you have to put in? Well, you have to feed the boiler. You have to burn some expensive coal or nuclear fissioning reaction to feed the boiler. And so then that gives it to you. So you're able to compute these two metrics of interest for answers for the backwork ratio and the thermal efficiency. Again, make a schematic. Label your states. Boiler, turbine, condenser, pump. 1, 2, 3, 4. Then put a table of properties. Each state should be able to get the temperature, pressure, temperature, quality, enthalpy, entropy. You could put flow exergy if you wanted to do exergetic analysis. You could do some other things like specific volume and internal energy, but these are the basics. All right. Then a table of energy transfers. What is my Q and W for each of the components? And then the key is to sum them to get the net for the cycle. Then compute your metrics, backwork ratio, and thermal efficiency. The pattern is the same as we march away from Carnot. All right. Here are the answers for this problem. Notice that we did get the negatives on the Q for the condenser, the negative on the W for the pump. We did get the Q net and the W net to match. Good to, I just showed 4 significant digits here. But because a lot of our property values in the tables are only given the 5 significant digits, you can't expect it to be more accurate than the data that you're given as inputs, S's and H's. And then we calculate a 30-some% backwork ratio. This is very high. And we get a 40% thermal efficiency. Now, we use this simple equation because it is a Carnot. The Carnot thermal efficiency is 1 minus the low temperature, or cold, divided by the high temperature, hot. And you use this very simple equation, you get the same thermal efficiency. The first time you do it, it's a jaw-dropping, eye-opening, I hardly believe this experience. I know it was true for me. It's like, you mean all of this work and getting these qualities and getting these S's and H's and all that, and then calculating the Q's and the W's, and then all that to get the efficiency, and then you just use one simple equation and you get the same answer? Absolutely true. Again, the Carnot thermal efficiency was derived at Thermo 1, but all of the heat has to be brought in at TH, and all of the heat has to be rejected out of the cycle at TL, low temperature. All right. This is a temperature entropy diagram for water. It's generated using the software RefProp. NIST was at National Institute of Standards and Technology, puts it out. You can purchase it as a student. You can get a free version. Just say student version free of RefProp on Google, and they'll take you there. And then you can download it, put it on your PC, and you can generate this plot. It's a little bit of work, but you can manipulate it. It's worth doing. So what do we have? Temperature on this going from 0, 100, all the way to 700 degrees C. We have entropy, the same type of units we have all the way out to 10. It's a linear plot. Look at the dome. It's surprising how symmetric that dome is. This is real data, not sketches done in like I do here in the class. This is real data plotted. Okay, what is this point up here? Critical point. All these saturated vapor. All these states saturated liquid. What did we plot here? Lines of constant quality, 50%, 25%. Okay. What about these blue lines, like 20 megapascal? What is that? It's a line of constant pressure, an isobar. Now, we just ran it with 8 megapascal, didn't we? You know, you could put a dot right here, saturated vapor, 8 megapascal. Then you could find the 20 kilopascal line, bring that across, drop down, straight down. There is state 2 on a TS diagram drawn to scale. State 4 is over here and drop straight down to 20 kilopascal, state 3. So the cycle goes 1 to 2, 2 to 3, 3 to 4, 4 over. What is all the heat brought in at? TH. What is all the heat rejected at? TL. This was what? 295 degrees C. This was about 60 degrees C. You add 273, you can do the efficiency very quickly that way. But that's a good piece of software, and hopefully I'll show a few plots. Here it is, the same software run where I was able to have the software overlay state 1 on the 8 megapascal, a little harder to see. And then state 2 to 20 kilopascal, hard to see. State 3 and state 4. All right. In the Carnot vapor power cycle, the fluid going into the pump is all vapor, all liquid, or a mixture of liquid and some liquid, some vapor. And show the results. It is a mixture of some liquid, some vapor. On the TS diagram, state going into the pump is state 3. Where is state 3? Right there. It's a mixture. Maybe the quality was whatever it was, 30%. Okay? All right. Guess what? If you're a design engineer, do you think you could make a boiler that boils water? Probably pretty easily. How about a condenser that condenses some water? Not too bad. Turbine that, you know, takes high pressure to low pressure, expands it, pushes. Yes, you're going to be difficult to have it perfectly reversible, but what about this pump? Good luck. No way. No way. Hey, what's the acronym in texting for no way? Like IDK? I'm learning. My wife, she was like, she said, what is that? She says, lots of love. I said, I don't think that's lots of love, honey. This was a while ago. She's now up on the lingo. But you're helping me come up on the lingo. So what is no way? Is there something like no way? You just have to spell it out? All right, fine. Anyway, there's no way they're going to build this pump. So guess what we do? We have a ideal Rankine cycle. And the Rankine cycle is moving away from the can't-be-built Carnot. You'll every now and then see that, say, why are the stupid engineers building these Rankine power cycles when they should be building the Carnot power cycle? We know the Carnot is so much more efficient. Yeah, good luck trying to build a pump like that, right? So what they do is they'll say, this condenser, let it condense. Let it come out here where it's saturated liquid. This pump is now HAPPY. Otherwise, that pump doesn't exist, and if you tried to feed a pump this liquid vapor mixture, it would be very unhappy. It would not work well. All right, so you bring this out as saturated liquid. Now, what does that do to state 4? Well, first of all, let's find our states again. Let's put here state 1. Did it change state 1? No. Did it change state 2? Somewhere down here. No. Where is state 3? Way over there. Where did 4 used to be? Way up here. Where should 4 now be? Right above 3. Because you're still going to have S4 is equal to S3, just like you had S1 is equal to S2. What do you mean S1 equal to? You have a great turbine. There's no irreversibilities. Hey, let's do the same for a pump. It's a great pump, no irreversibilities. Shouldn't S4 equal S3? Yeah. And so a lot of times a student will say, I know where 4 is. Right there. That's where 4 is. You think 4 is out there? Nope, 4 is not there. First of all, they have a lot of these blue lines. And every now and then it'd be like, well, what's out here? Well, this is where water's not happy. Water is just, it's not in a state of equilibrium. You can't have water at this entropy and this temperature. It doesn't, it's no. I mean, okay, you got 100 megapascal, keep going. Here's a bazillion megapascal and maybe a couple trillion megapascal. Maybe it gets out there, but normally no. Okay, engineering applications. These are the range of states for the fluid. In here, two-phase. Here, saturated liquid, saturated vapor, superheated vapor. This is even up in here, it's supercritical. You would call it like that. High pressure, high temperature, supercritical. This is behaving as ideal gas out in here. Yes, I could go with lower pressures. But, Professor, you didn't tell me where all these compressed liquid states are or subcooled liquid states are. Where are all those? They're all tucked right in here. Very thin. That's the extent of your compressed liquid or subcooled liquid states. They're just, all these lines get crammed in. And so, clicker question, I think I've already covered this, but in the ideal Rankine vapor power cycle, fluid going to the pump is, do you want the clicker question? Oh yeah, you like the points.
That's what we live for.
That's what you live for. You bet. What is the fluid going to the pump right here? Is it all vapor, all liquid, or some liquid, some vapor? All right, let's take a look. It is all liquid. It is saturated liquid. No vapor. No vapor. So now I need to talk a little bit about this pump some more. We're interested in this same W sub P. It should still be negative. I still need a negative answer, right? So I just gave you that one. It's going to be negative, okay? Always negative, not sometimes negative, sometimes positive. No, it's always negative. Now, when I do a control volume analysis around this pump, I have state 3 feeding it, state 4 coming out. Somebody says, I remember an equation allowed me to calculate that work that's out of a pump. Now again, that's getting the right sign, S-I-G-N. So WP. So is WP equal to either answer A, B, C, or D, your best estimate? I want to make a calculation of this work for the pump work. Which one is it? I'm going to pause and walk around. That way you have enough time. I want to see what other people say. So let's go ahead and we'll stop it now. Hey, a couple people need to get in.
Wait, do you want the magnitude or like the...
No, you need to have the right sign as well. Because what's the difference between, isn't this one and this one just a sign error?
Yeah.
Or a sign difference? Yeah, all right. Okay, everybody's in, we stop. Okay, now this brings up interesting. You learned, you were beaten into it. W is equal to integral PdV. Look familiar? And then you had this cylinder and a piston, and you could heat that gas that's trapped in this piston cylinder apparatus, and you calculate the work that the gas does by pushing back the boundary and pushing that piston away. True? And then you moved on in Thermo 1, and you moved beyond the CM analysis to a CV analysis. Control mass, control volume. You moved away from the closed, you went to an open. Maybe you had a pipe and a little box like this, and you had fluid flow in, fluid flow out, and you did a little. And this was a mind-bending, mind-warping change in Thermo 1. True? You're like, what? Now, we are doing analysis of a pump. Did I draw something like a closed or an open? It's open, 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 open. You need to look at chapter 6. It introduced entropy. And you did isentropic calculations of turbines, compressors, pumps, etc. At the end, near the end of chapter 6, they had a very interesting equation, W, and they put like int rev on it, minus the integral V dP. And they had changes of kinetic potential, but I knocked those off the equation. First time you saw that equation, you said, no, 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 this is correct. This is incorrect. Typo in book. Believe me, same for me. I said typo in book. I learned. I even was so proud. I went and got it tattooed on my arm. Integral PdV. But now I got to go get integral VdP. But is this correct? Is this okay? It is okay. It is a big equation. It is a big conclusion at the end of the chapter on entropy. So what you have to do is say, think about this. This is liquid water. It's saturated water, liquid, saturated liquid going in. What's going out? Compressed liquid. Okay, somebody gives you a job, says, I have a gallon of liquid water. It's saturated liquid water. I want you to apply pressure to it and make it occupy a volume of 1/10 of a gallon. Do you want that job? Gallon of liquid water, I want you to apply sufficient pressure so that it occupies 1/10 of a gallon. You know what? Liquid water is essentially incompressible. Incompressible. If it's incompressible, what happens to V as I'm going through the pump? You love that. Don't you take that constant outside the integration? Now you have the minus the V at state 3 or state 4, either one, they're the same. And then integral dP, isn't that P4 minus P3? Which one of these is correct? Ooh. Which one is correct? C. All right. Thank you very much for your attention. We'll pick up here next time. I'll be available to answer questions in my office.